Anyways, welcome of the universe. My name is Dennis Crabtree. I'm on the board of directors of the Friends of the DAO. I worked at the observatory starting in 1986 and with a few different adventures over the years. Anyways, I retired in January. So how many people here, is it the first time they're visiting? Okay, that's good to see. And how many people from out of town? Good number. Where are you from, sir? California. Whereabouts in California? Yeah, excellent. What brings you up here? Oh, okay. You, okay. Yeah, who else was that from out of town? Where are you guys from? Ontario. You're not from Toronto because you would have said Toronto if you were from Toronto. He did say Toronto. So, just to set you straight, this is the real center of the universe. Just to set you straight. Okay, so oh, it is your bag. Okay, no worries. Just sort out the seating here. So tonight it's my pleasure to welcome Andrew Schaeffer as our speaker. I didn't know he had so many friends, but Andrew grew up in Vancouver, did his undergraduate at UBC, master's at UBC, and then went to Dublin for his doctorate. And I asked him if he went there for the Guinness beer, and he goes, "No, but I enjoyed it while I was there." So Andrew is a research scientist with the Geological Survey of Canada. The building's up at Pat Bay, whatever direction that is, that way, I think. Andrew uses both computers and instruments to collect measurements of ground vibration and where they're from and how often earthquakes occur. I know he's been involved in various field trips during the summer up into the Arctic, and you were just off in some boat this year. So gets around, but also more importantly, Andrew is one of the co-runs the SchoolShake Program, which is a series of little centers around the region. We have one here on the observatory as well. So tonight, Andrew was to be talking about us from stardust to core. So astronomers, we look out, we see the stardust, we try to understand star formation, planet formation, and Andrew's going to talk a little bit about that by the looks of it. But after the dust is settled, so to speak, we pass it over to geologists to try and understand sort of more of the details. Another unique thing about tonight's, he brought us a Raspberry Pi. Oh, but it's got a Raspberry Pi in it. Thank you. Raspberry Shake. Milkshake, just raspberry. Yeah, sorry. So with that, let Andrew get on. Do you want all the lights down totally? Okay, lights out.
Is that working? Yeah, okay. Thanks very much, Dennis, and everybody for the invitation. So yeah, as Dennis said, these days I tend to look down rather than up. So what am I? I am a seismologist. So seismos, Greek, being earthquake or shake, study, and a person that practices that. So I study ground shaking and earthquakes, and we use those to study the inside of the earth. But what am I doing here? Well, actually, a long time ago, I did a co-op work term at, I don't know if you'd call it the sister facility, but if this is DAO, I did a work term at DRAO in Penticton, the Dominion Radio Astrophysical Observatory, which it wasn't that I didn't enjoy that and started to look down, but I explored a number of things. I did some glaciology for a while in the Canadian Yukon, and then I turned to seismology, where I spend most of my time now traipsing across the Arctic or working in the mountains around here on ships. And really, the boil I carry batteries into difficult places. That's what I do. And hopefully I usually have help to move those batteries around. So quick outline, let's start more with the astronomy side. So origins and journey of the Earth to what we have today. What does the interior look like today? And briefly, why is there life on Earth in the context of an ongoing Earth? Finish off, hopefully with enough time to talk briefly on earthquakes around the West Coast, earthquake preparedness, and touch on the SchoolShake program that Dennis mentioned. So let's start with stardust to rocky interior. So does anybody know what the age of the solar system is?
13 billion years. 5 billion?
Pretty close. I don't expect you to get it to that many decimal places. So 4,567.2 million years. So 4.5657 billion years, plus or minus 200 million years. Yeah, plus or minus 200 million years. Sorry, 200 million years for the plus and minus. So understanding how the solar system formed, we have to account for what we can see today. So that is that all of the planets, they orbit roughly along the ecliptic plane. That's the plane through the middle of the galaxy, the solar system, sorry. They're mostly anti-clockwise orbital paths, so they rotate around the sun in an anti-clockwise direction. It's called prograde rotation. So that means that most of the planets rotate on their axis in the same direction that they're going around the sun. As we go from the sun, as we step out, each time we go to a new planet, it's about twice as far as the last one. And then the sun has to account for 99.9% of all the mass in our solar system. So the theory for this is, we're not going to go into any details, don't worry, there'll be no exam at the end. Solar nebula theory. So this is the idea that what we have as our solar system today formed from a rotating cloud of dust and gas. Okay? And as it continues to rotate, it cools, it gets smaller, it contracts. As it gets narrower, the rate of rotation speeds up and it flattens to a disk. And that disk eventually becomes the ecliptic plane. After enough time, the very center of this rotating ball of gas and dust, it undergoes a gravitational collapse. It gets dense enough that it collapses on itself. And unlike making a black hole, this time we make our proto-sun. And we begin the thermonuclear fusion process that occurs in the sun. And it heats up. So here's both artistic renderings, but what's a great tool these days for these sorts of images is AI as well. This one is an artistic rendering of an early solar system where we have our proto-star at the middle, the proto-sun. We have this separation, so the frost line, this would roughly be where the asteroid belt is today. All the planets inside are rocky planets, and outside they're gas giants, formed from gas. Sorry? Yes, exactly. Yep. So again, AI, that's an AI rendering of an early solar system. Take it as you will. Nobody was actually there to see it. On the left, this is a computer simulation. So with computers today, supercomputers, we're able to model a lot of this sort of stuff. So do you mind just turning the lights off for this one? It's just a really dark video, unfortunately. I don't know if... Perfect. Okay, that'll work. Let's start this. So we have proto-sun in the middle. This video, I've had problems with this video stopping. Let's see if it keeps going. So we have the proto-sun, we have dust and gas circling around the outside. I think it's just too good for my computer. Let's see. And so what we have is these lobes, as you watch, they start to get smaller and smaller, and they start to concentrate. And so what's happening is this gas and dust is starting to coalesce, and these are forming planetesimals. So these are baby planets that are forming around the sun. And this is simulating predominantly just the early inner solar system. So these would be the rocky planets that are starting to form in the interior part of our solar system. Okay, so, I let it slip. Anyone know the age of the Earth? If you're really fast, you already saw it. Yeah, okay, I messed that one up. Okay, 4.54 plus or minus 0.05 billion years, so 50 million years, plus or minus. So that's about 100 million years younger than the solar system itself, and this is a time scale of all of Earth's geologic history. We're not even a millimeter on the far right-hand side, and so here we are at 4.54, and this is called the Hadean Eon. And so this is the very beginning of the Earth. This stage, Earth was, it was a liquid, it was a magma ocean, both at the surface, it was a magma ocean in the interior. It was magma everywhere. Yeah, wouldn't have been very comfortable. So it's really hot, and this heat is from the accretion process, it's from radioactive decay, and it's from energy of the collision of all these little planetary bodies to form the one bigger planet, what we call Earth, or this would be similar for Mars, Venus, Mercury. And the surface temperatures at that time likely exceeded 2,000 degrees Kelvin, so it was very hot. And once again, you can find all sorts of what an early magma ocean Earth would look like. You'd have lots of asteroids and meteorites impacting. There'll be magma and volcanic eruptions everywhere. So, next question. Does anyone know where our moon came from? Yeah. There's a number of theories for it, for where the moon came from. So, is it an asteroid that the Earth captured? Is it due to an accretion event? So this would be a separate body that formed from the dust cloud. Or could it be from fission? So fission would be the proto-Earth throwing off a little body. Well, we know that it's most likely not those. We can look at the rocks of the Earth and the Moon, and we can see how their compositions evolved over time looking at radionuclides. And we know that they had to evolve in a particular fashion in a similar way. So we know that it can't be those, and so the prevailing theory is the giant impact theory, and that is that a Mars-sized protoplanet, which has been called Theia, impacted the proto-Earth early on in this Hadean Eon. And as a cartoon, this is what's proposed. You have Theia, you have the Earth, it impacts, it produces a disk of debris, and that debris coalesces to become the moon. And similar to the previous video, here's another video now created on a supercomputer modeling, let's get it to play, the impact of a small planet. These are both molten planets. Essentially, you collide, you form this big ejecta of material from that the Mars-sized planet, and it is still gravitationally attractive. Actually, this is not the moon. That one will become the moon over there. This one's going to get sucked back into and become part of the Earth again. And this whole process in real time, simulated time, it's less than a day for that process to happen. Okay, so let's keep moving forwards. So Earth doesn't look like that anymore. So how did we get there? So what does the process of the Earth looking like today look like? Well, we have to form something solid that we can stand on. So we need to start taking this molten ball of magma, start to cool it. And when you do that, you get a differentiation process. So that is, you separate the Earth into different layers, the surface and the interior. So the heavy metals that are inside the Earth, those sink right down into the center. And the lighter materials, these are the silicates. These are what our rocks are made of. These float, and they come up to the top. Okay, and as we continue to cool, we start to form a crust. This process, over a lengthy amount of time, generates our core, our mantle. This is the middle part of the Earth, and then our crust. And both the processes of forming these features, but also their existence today, this is played out in the geologic activity that we see on the Earth today, that we can observe. It ties all the way back to the way that the Earth formed. So the plate tectonics that we have, volcanoes, the Earth's magnetic field, it all comes from these early processes. Sorry? It is all linked, that's absolutely right. Oh, okay. So let's look inside the Earth. So this is a schematic diagram. The part on the right-hand side, as you can see, is not to scale, is to scale. So we can't see the crust at all here. It's thinner than the line on that plot. So at the outermost part, we have the crust. It's on average 7 kilometers thick. This is the part that we live on, right? This is the part that the ocean sits on. It's only 7 kilometers thick. By percentage of the volume of the Earth, it makes up only about 1%, and about 0.5% by weight of the Earth. The mantle is this part, the orange part on this plot. This is largest part by volume, so it's almost 3,000 kilometers thick. 83% of the volume of the Earth and almost 70% of the total mass of the Earth is contained within the mantle. And then we have the outer core, just over 2,000 kilometers thick, only about 15% by volume, and the inner core, which is quite small, 0.7% by volume of the whole Earth. And we'll talk briefly about these layers. First of all, how do we know what those layers look like? We can't obviously see them, so we need to have some sort of remote sensing method that we can look down into the ground. And that is what I do, and one of these methods we can use is seismology. So here's a cross-section through the Earth, and this plot has the two main types of seismic waves. We have P waves. Those are pressure waves, so those are like sound waves. They're a compressional wave that travels. It can go through solid material, it can go through water, fluids, that sort of thing. The black ones, these are shear waves. They travel slower. And they have the motion of a particle is perpendicular to the direction it's traveling. So when you feel an earthquake, it's typically the shear waves or the surface waves that you feel. These are the ones that actually cause the shaking. And what's important is that the shear waves can't travel through a liquid. If I said the P waves were red, I got that wrong. I'm not sure if I said that, but it's the other way around, sorry. The point is S waves can't travel through a liquid, and black travel through the liquid, so they cannot be the S waves. Okay, so that was a very simple diagram of the various waves. I'm just going to show another video here. This is a much more complicated, this is what we would call a wave field simulation. Okay, and so I'm going to pause it just as it starts. Where's my mouse gone? Okay, so this yellow and red pulse, this is the P wave traveling out from an earthquake that happened. And the blue and the green is the S wave. And so the P wave is going out faster. It travels roughly spherically, and it travels faster. Okay, and so these would be the ray paths that we saw from the previous diagram. And we have two seismograms at the top. This one recorded here, and that one recorded there. And it's just to show how complicated the waves get quickly as they travel inside the Earth. We don't need to worry about any of these details, but this is to say this is how we model and image a lot of the details inside of the Earth, is we use not only those first arriving waves, which are simple, but we use all the combination and superposition of these later arriving waves to look at where and the properties of all the layers that are inside of the Earth, along with, of course, with the help of computers. Okay, so quickly going through the Earth's layers. So let's start with the crust. It's thin, it's rigid. You know, we can step on it, we can stamp on it, but it does deform over very long time scales. There's two types of crust. We have oceanic crust, and this forms at our mid-ocean ridges. It's fairly low density as far as rocks go, 3.3 grams per cubic centimeter for reference. Water is 1, so it's 3 times heavier than water. This one's pretty easy. You know, we can all pick up a rock. We can feel how heavy it is. The oceanic crust is thin, no more than 7 kilometers typically, and it can be as old as 200 million years or as young as being made today. So just offshore at the Juan de Fuca spreading ridge, we're making brand new crust all the time. We also have continental crust, and this is created through repeatedly recycling oceanic plates. We subduct it, we melt it, we make volcanoes, and what comes out of those volcanoes becomes our continental crust, which is a bit less dense than oceanic crust. It can be typically 20 to 50 kilometers thick. It can be thicker. So for example, in Tibet, the Himalayan mountains, where we're building these very large mountains, the crust there is actually 70 kilometers thick. So it can vary quite a bit. And the age of the crust, it contains some of our oldest rocks on Earth. These can be about, currently the oldest rocks that we've found are about 4 billion years old. We have, you'll see older dates around. Those are specific individual grains of certain crystals inside those rocks. So those crystals are 4.3 billion years old, but the rocks that they're in, they were produced only about 4 billion years ago. So if we take, and then beneath the crust, as shown here, we have what's called the lithosphere. And this is a part of the mantle, but it's more rigid than the rest of the mantle. And so together, the crust and the lithosphere make up our tectonic plates. Plates on the outside of the Earth that we live on, and these move around, which we'll come to in a bit. Okay, the Earth's mantle, it's its dynamic layer. So its density and temperature increase quite a bit with depth. It's got a low thermal conductivity, so it has to cool itself by convection. And so this is a simulation on the right of a convecting mantle within the Earth. And this is another computer model. The blue is cold, the red is hot. So the core would be on the inside, and this would be where our crust is. And essentially we have all of these blue drips. So this is material that's more dense and sinks compared to this material, and the red is more buoyant, and so it rises up from the core mantle boundary. It's just like a boiling pot of water in that sort of sense. You have the hot water from the bottom of the pot rising up, and you have, it's still hot, but relatively cooler water replacing it at the bottom of the pot. So the upper mantle is, the mantle is typically separated into two layers with that transition at around 410 to 660 kilometers depth. And this is a key layer. We won't go into details on it, but it's a very key layer within the Earth that actually moderates how far some plates subduct into the Earth. Not everything goes right down to the core mantle boundary. Some subducting plates actually get stuck in the middle of the mantle. This produces a lot of interesting volcanism. The mantle rocks, as I said before, they're more dense than the crustal rocks, and the temperatures can go from 1,000 degrees Celsius to almost 4,000 degrees Celsius within the mantle itself. Okay, moving deeper, the outer core. So it's made of liquid iron and nickel, and it's very dense. So, we're now talking 10 to 12 times heavier than water, and its temperatures go from 3,000 to 5,000 degrees Celsius. What's important about the Earth's outer core is it is home to the Earth's geodynamo, and that actually produces our magnetic field. So we won't worry about the details, but essentially because this is a fluid moving, a moving metal is like electricity in a wire, which produces electric fields, which produces electric currents. And this, because of how big it is, makes the magnetic field that extends beyond the crust of the Earth and extends outside of the Earth and actually protects us from the solar wind. So interestingly, the core is rotating faster than the rest of the outside of the planet, and it's this faster rotation that actually helps make the geodynamo and stabilizes our magnetic field. And finally, interesting fact, so because the Earth is continually cooling, that's why we have mantle convection, what we actually have at the inner core boundary, where is it here? So right here, the inner core is actually slowly growing out at the expense of the outer liquid core. And that's because essentially the bottom of the liquid core is freezing to the inner core, freezing at 4,000 degrees Celsius. But that's because of the high pressures that it's under. And so the inner core grows in radius by about 1 millimeter per year. And at that radius, that's equivalent to about 80,000 metric tons of iron per second being added to the inner core. So the inner core, it's a solid iron nickel sphere. Its density, however, is less than that of a pure iron nickel alloy. So what that means is there's got to be some other lighter elements in there too. And this is an active field of study. We don't know exactly the relationships between them. We know that it's about 80 to 85% iron, 5 to 10% nickel, and the remaining 5 to 10% is made up of silica, sulfur, oxygen, carbon, hydrogen, and phosphorus. But the relative proportions of those are very, very difficult to nail down, of course, because we can't actually go sample them. The temperature ranges from 5,000 to 7,000 Celsius, and the actual existence of the inner core wasn't hypothesized until 1936 by Inge Lehmann, who was studying the way the seismic waves reflected off certain features, and she deduced that there must be some solid crystalline structure beneath the liquid outer core. And it wasn't till the 1980s that this was confirmed using observations of normal modes. So there when a big earthquake happens, the whole Earth shakes. It contracts and it expands in certain orientations, and those allow us to study the very, very deep Earth. So it's very recent, actually, that although it's been theorized for quite a while, it took quite a long time to prove this. And interestingly, very recent, ongoing research, in fact, suggests that there's actually an inner core. And that is, there's the very central portion of the inner core has different seismic properties than the outer part of the inner core. And this could be to changes in the type of iron crystals that are there. It could be how those crystals are aligned. We don't know yet, but there is a boundary inside the inner core as well. Okay, so life on Earth, without going too heavy into why is there life on Earth, let's just cover two things. So we got the Goldilocks zone, and we have our dynamic interior. So for the Goldilocks zone, it really is that we are just the right distance from our sized star. So here we are on Earth, and we're in the habitable zone. So that is that we get the right amount of solar radiation for the size of our star and the distance we are from our star. Okay, so that's quite important. Similarly, we have our dynamic interior. So that produces our magnetic field. And our magnetic field, when you look at a perfect magnetic field, they're symmetric. Ours is not symmetric. And that's because it's constantly bombarded by the solar wind. And so it's essentially being driven down the highway. Perhaps the Autobahn maybe is better, and it's being distorted away, but it's protecting us from most of the solar radiation. Combined with this, we also have our mantle convection that helps regulate surface temperature. It recycles surface materials. I don't mean aluminum cans, but rather we take our rocks, we take carbon, we pump it back down into the Earth. This gets brought back up through our volcanoes, and this helps sustain our atmosphere. So together, these two processes really help sustain life on Earth, maintain our atmosphere. Okay, so I wanted to finish by just talking a little bit about living in an earthquake zone, since that's what I do for a living, and I also live here. Okay, so we live on the edge of a plate. So it's, it's pretty clear. We live, those of us that live here live here. California, you have your own brand of earthquakes. So you can see all these blue and colored circles. This is a global catalog of earthquakes, and you can see they trace out patterns on this map, a bit like a jigsaw puzzle. And those earthquakes, for about 95% of them, concentrate along plate boundaries. So most of our earthquakes happen at the boundaries between tectonic plates, and we live, I'll just back this up, we live right here. Where's my mouse? There it is, Cascadia, right in here, Cascadia subduction zone. And here on the West Coast, earthquakes are a part of life on the West Coast. We have small earthquakes here every day. We have damaging earthquakes that can be decades apart, and we have the potential and have had some of the world's largest earthquakes, but these are centuries and centuries apart. And there's lots of indigenous stories, oral histories, and for example, this is the earthquake mask that's at the UBC Museum of Anthropology. So it's established in oral histories and oral traditions, the history of earthquakes here. So what do we have on the West Coast? So we're situated here in Victoria. Here's Vancouver Island. So we have three main types of faults and boundaries between our plates. We have plates that collide, so that would be the Cascadia subduction zone. We have plates that move apart here. That would be the Juan de Fuca spreading ridge, making new oceanic crust. And we have plates that slide past each other. So that would be the Queen Charlotte Fault up by Haida Gwaii here. So that would be a strike slip fault. The subduction zone that we have here produces the volcanoes that are part of the Ring of Fire that goes all the way around the Pacific Ocean. And so let's talk just a little bit about the subduction zone. So that's this trench that goes from roughly middle of Vancouver Island all the way down to California, and it's the interface between the North American plate right here and the subducting Juan de Fuca plate. And so it gets locked, it gets stuck, it stays locked for some hundreds of years, and then it slips, and we have a large earthquake. There's a number of ways that we know about that, because we haven't, in our lifetimes, experienced one of these. So one of the ways that we can look back in time, there's a great saying, I can't remember if it's on the floor or on one of the stands, but your telescope allows you to look back in time. Although geophysicist, not a geologist. Your geologist would say that sediment records, which is on the right-hand side, are the equivalent way of looking back in time. So we can look at evidence along the coast to see evidence for past large earthquakes. And so what we're seeing here is a ghost forest in Oregon. So when you have a big earthquake, you actually cause the leading edge of the plate to move up and down. So this is a ghost forest that was created. It was above land, the big earthquake happened, and it was suddenly drowned by both the tsunami, but also the ground surface dropped by 3 or 4 meters. And so it became a tidal marsh. And these types of trees don't survive in brackish salt water, so they died. And then over the next hundreds of years, that area got lifted up again, and so they're not underwater anymore. So by studying the sediments, which if you want to look at the end, I've got a couple peels of sediments from the west coast here that show the earthquake that we're going to talk about in a second. We see that there's about 19 major earthquakes in the last 10,000 years, on average 500 years apart, with a range from 250 to about 850 years. Now, the last major earthquake here was the 1700 Cascadia earthquake, and we actually don't have any precise estimate for exactly when it occurred here. However, we know that it was at 9 time on January 26, 1700, and that is because of the tsunami records in Japan. And so there's a record of a tsunami in Japan at that time that did not have any local earthquake. There was no shaking in Japan, so they knew it had to be from somewhere else. Now that we can model tsunamis, we know that it takes around 10 to 15 hours for a tsunami wave to travel across the Pacific. We can say precisely when that earthquake happened on the Pacific coast because of the records that were kept in Japan. I don't know the numbers, actually. I don't know that we have a good sense of the numbers for that sort of earthquake because of how long ago it was. Yeah. Okay, but it's not all doom and gloom. So mitigation and preparedness. So we can prepare for these sorts of things. So we have, we build right. So we have building codes. We have reinforcement of those codes. On a personal level, we have our emergency kit and a plan for 2 weeks. So if you want insight into what to do, you can visit Prepared BC, Public Safety Canada. I have to admit, I can't remember what ICLR is. Apologies. But you know, you have your emergency kit, camping supplies make good emergency things, shoes and flashlights. We are all much more familiar now with N95 masks than we were a number of years ago, and when you have a lot of stuff shake, you make a lot of dust. So, you know, keeping a few N95 masks kicking around is not a bad idea. And basic things around your house. Secure your space, so make sure your tall and heavy furniture is bolted. Heavy appliances, loose items, your pictures and mirrors. Don't have your huge, beautiful painting loosely above your bed. Make sure it's well attached to the wall, and keep heavy items low. There's also now, which some may have seen this announcement, there's now a Canadian earthquake early warning system. It actually went live in BC on May 9th, 2024, so earlier this year. If you want to know why it was only announced in August, you can ask me after the fact when I'm not being recorded. So what is earthquake early warning? Well, it's proven successful in many other countries. It detects P waves, those are those fast arriving waves, and sends an alert to people and to systems. So that yellow wave is the P wave. It's picked up by sensors. They send the data to the data center, and it sends out an alert, both to people, but as well as to infrastructure. So for example, you can bring trains to a stop before the really damaging shaking arrives. You can open fire hall doors before they get bent and can't open, this sort of thing. So even a few seconds can provide for when major shaking occurs. Now, for public alerts, these are distributed via NPAS, so that's our National Public Alert System. For magnitude 5 earthquake, certain amount of ground shaking, it's called MMI4. This is the system that currently we get alerts on our phones for weather, amber alerts, those sorts of things. And it'll go to your cell phone, but it'll also interrupt radio and television broadcasts. And you know, when you receive that alert, drop, cover, hold, as we practice or have practiced, and stay in that position for a good minute or two, because depending on how far away you are from the earthquake, it's better to be safe than think you're clear and then the shaking arrives. So Yeah, for a large earthquake, there will be aftershocks. Yeah, yeah. They won't be usually. Typically, they won't be as large as this, but there will be aftershocks afterwards. Yeah. Okay, and I'm going along here, but I'll quickly just say a few words on SchoolShake. This is an outreach program between UVic and the GSC with support from Hakai and a few other institutes. So this is trying to take education outreach to the classroom. So shaking up earthquake education using citizen seismology. So the vision of the program is to engage school-age children in STEM subjects and with a prioritization on schools with underrepresented populations in STEM areas. Highlight the geoscience as an exciting and interesting career option. We're seeing declining numbers, and we need to try to address that from the bottom up. Increase community resilience, again from the ground up, through educating younger generations, and as well with some science aspects, expand our local network, better understand our local faults, that sort of thing. So this is all made possible by the Raspberry Shake seismograph, which I have one on the table here. When we're done, feel free to come up and take a look at it. It's got a geophone sensor, so that's what measures the ground vibrations. It has something to convert those analog signals to digital counts, and then it's all based on a Raspberry Pi, so this little computer. So it's all very small. It's about this big. And Raspberry Shake actually has deployed a global network. So it's a citizen science program. They don't deploy them. You can buy them. Their 1D version is $300 US. So all of these instruments are predominantly put out by hobbyists, citizen seismologists, and then a number of these are put out by organizations and other interested parties, so you can do some research with these as well. So it's a large global network. There's more than 2,200 stations around the world right now, just Raspberry Shake. So what we've done is we've deployed these predominantly in the Victoria area. We also have some in Campbell River, as well as Haida Gwaii, and we're currently working to expand to the Lower Mainland, as well as the Yukon. And then we add to those, on the right-hand side, this brings in the Canadian seismic stations as well, to try to fill in and build and just provide more data and more context to build a more complete picture. I won't spend any time on this, but just to say that we provide at no cost resources for teachers. It's curricula for grade 8 and grade 10. Grade 8, I think it's grade, I can't remember if it's grade 8, grade 10, or grade 11, but we have 4 lessons for grade 8 and 3 lessons for grade 10 or 11, including PowerPoints, teacher guides, that sort of thing, that make use of the Raspberry Shake and provide very detailed help to bring that sort of stuff into the classroom. And then we're also available, both myself and my colleagues at UVic and our team of grad students are more than happy to come to the classrooms and give presentations, that sort of thing. And finally, I'll end with this slide just to say that with these SchoolShake instruments, it's not only about outreach. There's a lot of earthquakes that occur in southern Vancouver Island, and some people from living around here might have heard about the Elk Lake fault that was discovered last year. And so we don't really have a good idea of how many earthquakes occur on these small faults because they don't typically, we haven't had the density of sensors to actually look at it. But with programs like SchoolShake, which are the green triangles in this image, we have enough stations that we can actually start to look for what would be microseismicity on these faults. So, these are magnitudes less than 0 that nobody feels, nothing is impacted by, but tells us whether something's active. I'll leave it here, and just if we put the lights on at the end, if you want to come and look at the tsunami peals, I'm happy to talk about those, and we can pass around the Raspberry Shake. With this many people, oh, okay, sorry.
Before we take questions,
Yeah. Well, should we try jumping with this many people in here?
We're going to do a little experiment.
Yeah.
So everybody needs to stand up, if you're not already standing. And what we want you to do is on the count, and what we want you to do on the count of 3 is jump in the air. So the idea being that all of us jumping together generate enough shaking that
So yeah,
a little instrument in our building will be seen.
and so it's going to be this one, We don't know. We haven't tried this. So it's the building over there, different building, but we'll see if all of us jumping at the same time in here is enough to register on the instrument in the other building.
I think it's Dell or somebody playing in the Seattle Dome.
Oh, it was Taylor Swift, actually.
Taylor Swift.
Yeah.
Sorry, thank you, Taylor Swift.
It was I think it was a magnitude 2.3 earthquake, something like that.
We're not going to generate 2.3.
No.
Okay, everybody ready? So on the count of 3, jump. 1, 2, 3, jump!
And now we wait. Yep, there it is.
Yeah! Which one is it?
Sorry?
What is it?
It's this here, just coming in.
Oh, there it is, right,
Right here.
Yeah.
Yeah.
So there it is at the end. Very strong signal.
That was great because I wasn't sure it was going to work.
That was easy.
Yeah, it was easy. We can do better.
Do it again.
Okay.
Okay, you want to do it again?
Yeah.
Okay.
Good. On the count of 3. 1, 2, 3. And we wait. And
Woo! Bigger.
okay, very cool. Okay, sit down. And we'll take a few questions. Yes, sir.
Well, before you ask, can you just briefly repeat the questions?
Oh, yeah, sure. Yeah.
So have you studied any of the infra earthquakes where maybe 8 to 10 frequency per minute, also being associated with they've seen quakes on the sun and electromagnetic. So there's, and I read Sky elsewhere, and I actually seen these 2 different articles, and then about 3 years later they went, they're connected.
Interesting.
Have you read any?
I am not. I don't know any details about it. Often what we see is correlations that are difficult to determine causation. So I don't know the details of that article. So I would say that certainly there could be those events on the sun. I don't know myself how well or if they're tied to earthquakes that we observe on Earth or not.
They're the infra earthquake. There were only 8 to 10 movements per minute.
Oh, yes,
Slow,
yes, okay.
And they're having these, because the sun has earthquakes
Yes.
as well, where they're like rings like a bell with CMEs and stuff.
Right. Yeah, no, I don't know in detail. Sorry. Yeah, it's different branch of seismology completely from what I do. Apologies.
Okay.
Yeah.
Back there, question.
There's huge also earthquakes off Vancouver last month. Where's this the biggest?
Which was the biggest? It was a 6.4. Yeah, and that would have been I believe it was the Savanco fracture zone. So it's one of the transform faults towards, it was up towards northern Vancouver Island. Yeah, those ones, yeah. That's one of the most seismically active parts of Canada, is that area offshore. And they're pretty much limited to magnitude 6.5. They can't usually get much bigger than that. The size of an earthquake depends on the area, the surface area of the fault that ruptures, and the length of the faults there are limited by the length of the transforms, so they can't really get any bigger than that up there. Yeah, and they're unrelated to Cascadia, essentially.
So Cascadia tsunamis going to North Vancouver here too.
So a major, like a whole Cascadia rupture would produce a tsunami. It doesn't have a huge wave that comes in beyond, like into Vancouver or anything like that, but there is some inundation in Puget Sound. Yeah, I don't know precisely the wave heights or anything like that, but yeah. Would the Cascadia earthquake? Yeah, those would be your magnitude 9s. Yeah, or they could be magnitude 9. Like if all of Cascadia ruptured, it could be a 9.5. Yeah.
Yeah, okay, just going back to the structure of the Earth.
Yeah.
Every once in a while I'll see articles about, that talk about the metal core.
Yeah.
Spin is changing speed, and it even hints at flipping the magnetic poles. Can you comment on that?
We do. So yeah. So the pole, so north and south pole on Earth, flip back and forth quite often. Well, you can actually see it. It's called the magnetic striping in the seafloor. So when seafloor is extruded at an ocean ridge, it's molten and it freezes. And the crystals in the molten rock align with what the magnetic field is when they're liquid, they freeze. But then every kind of, it's not a constant rate, but it varies from 50,000 to some millions of years, it'll flip. And so then suddenly you have a band of oceanic plate where it's recorded north-south. And so you see this striping, they're called crons on the seafloor. And so there's I don't actually know how many, but there's it's continuous. And there's some evidence that would suggest that we are perhaps approaching a change in the magnetic pole, but it's a process that is almost impossible to model. So we don't actually know how fast or slow it happens. Like, is it a year? Does it take 10 years, thousands of years? We don't know because there isn't very good resolution on the dates of these boundaries in the rock. When we date a rock, it's usually, a good date would be plus or minus 1 million years, right?
Yeah.
So you could say we're well in the decimal places.
I've seen at least 10 of those articles in
Yeah.
the last few years.
Yeah.
And I'm like, okay, so right, like, what does
Yeah.
this mean to us?
So we don't really know. I mean, we can see our pole is wandering quite quickly, but
Right.
does that mean that it's going to suddenly shoot to the South Pole? We don't know when.
Okay.
Just that at some point it will.
Yeah. All right.
Yeah. Yeah.
Is it possible to get a copy of your P-Wave slide? I'm the public educator
Oh,
for Victoria.
sure.
I'd love to.
Yeah, absolutely. I can give you a card and you can email me. So it's off of the P-Wave slide is from Oxford Seismology Group YouTube.
Yeah, because we have
Yeah.
all the extra parts for the.
Of course.
Yeah.
Yeah,
so-
for sure. No problem.
That'd be great.
Yeah.
Yes, sir.
You had a slide on the dynamic layer.
Yes.
So is that force self-moderating between the heating and the cooling area? It kind of looks like it's cooling itself whenever it overheats.
Yeah. So this is not technically the Earth. It's actually modeled as a cylinder, which of course we're not, but same idea. So essentially, the core is really hot. So it does self-moderate in a sense. I mean, the Earth is very, very slowly cooling in total. But the mantle temperature, has not changed significantly in the last 100 million years. It's quite a slow process. But yeah, essentially, the blue drips are, they get dense enough that they'll just drip back down into the mantle, either as subduction zones proper, where they subduct in, or you can actually get areas of the continental interior, which we call delamination. And so that's that lithospheric mantle. It can be, we call it refractory, so it's very depleted, so it's actually quite dense. And it can get dense enough, it's a very fine balance between chemical density and thermal buoyancy. But you can get to this fine point where suddenly it's just dense enough compared to how much the elevated temperature around it. It can actually essentially peel off the bottom of the continent and it will drip right down into the mantle. But those cooler pieces dripping down do moderate and eventually result in the slow cooling of the interior. Yeah.
One last quick question. Yes, sir.
Yeah.
I don't know if it's quick, but.
That's a good preface. That's okay.
What pieces of information or new technologies do you think that we need to discover in order to best predict future earthquakes or understand what's happening?
Yeah, so very good question. Yeah, jump to the meat of it. So one thing we'll say is that we will never predict earthquakes. It's a term that we don't like to use. The best case we'll get to is forecasting. And so the challenge is...
Better than weather forecast.
Yeah, fortunately we work in hundreds of years, right? So the challenge is that we will never know, to model when a rock is going to fail. So when a fault is going to fail, you have to really understand the full frictional history of that fault to be able to say how close is it to its failure point. So you can calculate what the failure stress would be, but you need to have modeled the whole history of the fault to know where it is relative to that failure point. And so big earthquakes like this that actually rupture that fault, they don't occur often. I don't want them to occur often, but they don't occur often enough for us to actually have any data to model when that would occur. So one of the reasons why we want to look at microseismicity is that on any given fault, there is scaling relationships as a function of the magnitude of earthquake. So if you can measure lots of little ones, it doesn't mean that the little ones are relieving the stress, but there's empirical relationships you can use that if you have this many magnitude zeros, this many ones, it gives you an inference on how frequent the larger earthquakes are. So the best thing that we can do is essentially put out as much instrumentation as we can to understand the microseismicity, to fill in that magnitude gap. And then the other thing that we can do is our preparedness. That's really what we have. So mitigation and preparedness. Essentially here, I mean, it's not to be doom and gloom because it's not that, but it will happen eventually. I don't know when, but there will be a large one. Maybe not in our lifetime, but there's a 30% chance of a damaging earthquake in the next 50 years. Here.
How long have we been saying that?
Pardon?
How long have we been saying that? Because that's what I teach.
It's probabilistic, so it kind of it doesn't change very quickly year on year. Yeah. Yeah.
Okay, let's thank Andrew.
Yeah. Oh yeah.